Hello, in this video I'm going to be solving problem 2 from section 15.1 of James Stewart's Calculus Early Transcendentals. In this problem, we need to use a Riemann sum with m is equal to 2 and n is equal to 3 to estimate the value of a certain double integral. And the problem wants us to use Riemann sums with sample points that we take to be, for part A, the lower right corners of the subrectangles, and for part B, the upper left corners of these rectangles. So, okay, how do we estimate the double integral? Well, recall that when we're estimating this is going to be, or actually, let's suppose that, or no, what am I trying to say? In general, when I'm estimating a double integral, this will be this double sum here. This is a j, f of xi, yj, times my delta a, where the points are the sample points I'm taking. And so here, well, they give us the sample points geometrically, so we should probably draw a grid of our rectangle R and the subrectangles that we get. So let's draw a rectangle R. So it'll be like this, and then like this, going up to 4, and then 1, 2, and -1. There we go. So our rectangle is going to be this guy right here. This is 4, this is 2, this is -1. And the subrectangles that we're going to get when we divide this, well, in these problem statements, m corresponds to the number of subdivisions for the x part, and n corresponds to the subdivisions for the y part. So we're going to divide the x section into 2 equal pieces. So here we divide it along 2. This is 2 right here. And, well, from the length of this interval is 3. And because we're dividing it into 3 pieces, we're just dividing it along this way right here. So our subrectangles are going to be these. This, 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 and this. Now, for part A, we want the lower right corners. And these lower right corners are going to be, well, actually, let me make a copy of this first. This whole drawing, because we're going to need a copy of it for part B. Duplicate, and there we go. There's my copy for part B. But for part A, they want the lower right corners, which are going to be these points right here. And if we list these out, well, the points are, well, just going through the points, we're going to get -1, 2, or 2, -1, 2, 0, 2, 1. And also, the other points are going to be 4, -1, 4, 0, and 4, 1. And so the approximation for this case, let me move down this diagram right here. This approximation is going to be, well, we're going to have double integral of r1 minus xy squared dA is approximately, and what we're going to do is we're going to add up this quantity here over all of our points, and you'll see what I mean by this. Actually, wait. First, we need to determine what delta A is, because you might notice up here that we have this delta A. That's the area of each of these rectangles. And because we're splitting up our domain into equal rectangles, delta A is just going to be the same constant for each of these. So my delta A, well, we can see from this diagram that the area of this rectangle is 1 times 2. So, or 2 times 1, which is 2. And so the approximation I get is going to be, all we're going to do is we're going to take our sample points and we're going to add them up. We're going to add up f at those sample points multiplied by the delta A. So we add up on and on and on up to until we get to the last points, delta A. Now for this problem, it's actually pretty nice because, well, the delta A's are all the same. And, oh, I should mention that here I'm letting this be f of xy. Because the delta A's are all the same, we can just factor this out, and this becomes f of 2, negative 1, plus f of 2, 0, plus f of 2, 1. And I'll write out the whole sum here. 4, negative 1, plus f of 4, 0, plus f of 4, 1, times our delta A, which, if you'll remember, it was 2. Let me write a note of what we did here. This is this. And going to a calculator, what we find is that this last expression works out to be exactly negative 12. So that would be the approximation for when we use the lower right-hand corners. Now let's do part B, where we do the upper left corners. And so we'll do this here. Oops. For part B, once again, we want the upper left corners, so that's going to be these points right here. And so now, listing our points, well, they're just going to be 0, 0, 0, 1, 0, 2, and then 2, 0, 2, 1, and 2, 2. And so then, our approximation, well, first, again, we set it up. It's going to be r1 minus xy squared dA, where once again, this is my f of xy. This will be, we just add up the function values at all of these points, and we multiply by delta A. Note here that delta A remains the same because the areas of the rectangles have not changed. So we add up at all the points, but this is just f of 0, 0 plus f of 0, 1, after we factor out the delta A, of course. Delta A, which is equal to 2. And on the calculator, this works out to be negative 8. So this would be the approximation if we use upper left corners instead. I think it's pretty interesting to note that if you were to work out the exact value of this double integral here, it adds exactly negative 12. Like even without an approximation, if you work out the exact value of this integral, it works out to be negative 12. And so it's pretty interesting that this approximation actually gives us the exact answer, but that's more than likely a coincidence. In general, whenever you approximate with a Riemann sum, you're only going to get an approximation to your integral. And we already see that here because, well, this disagrees with what the claimed value of this double integral actually is. Okay, that's it for this video. If there are any questions, please feel free to leave a comment. Otherwise, I'll see you all in the next video.